Okay, so let's start. In the last class, we were looking at some simple problems where we applied the information theoretic tools that we've seen in class to a bunch of problems. And we saw a couple of applications. One was this puzzle or a simple problem where the goal is to estimate something using binary or ternary measurements, and these information theoretic tools can allow you to derive lower bounds on the minimum number of measurements used to estimate or recover some particular unknown quantity. Right? We'll see another simple example. Again, something that is a problem in the Cover and Thomas textbook, and see how these information theoretic tools can tell you something, can also help you derive lower bounds on whatever quantity that we're interested in. So the context in this case is random number generation. So when you're using a random number generator, some function like rand or randn in Python or MATLAB or any programming language of your choice, what is typically generated is not a real random number, but rather a pseudo-random number. Right? So there's typically there is some kind of a finite state machine which usually generates uniform random bits. Right? But then you have these various libraries that can typically generate numbers from different kinds of distributions. And the standard approach is that you have a random number generator that produces, say, numbers according to some distribution, some fixed distribution. If you want to generate according to a different distribution, then you try to transform one distribution to another. Right? So as a simple example, suppose that you have a random number generator. Somebody gives you a random number generator that generates uniform random variables. Right? You can generate any number of random variables which are uniform, right? And perhaps IID. I'll start with the example of continuous, but then we'll go to discrete. I suppose you have uniform random numbers. How do you generate a random number from another distribution? Let's say Gaussian distribution. All right. Have some of you seen this before? Correct. So how do you do that? Yeah. Correct. So suppose now you want to generate a random number x, which is distributed according to some other distribution. Let's say you want it to have PDF fx or correspondingly CDF fx. One simple way is you have u and you set x to be equal to fx inverse of u. All right. So this will have distribution fx. I'll leave it as an exercise for you to show that this is indeed the case. Okay. So these are sort of standard techniques to generate random numbers according to whatever distribution you want. But firstly, you need to be able to generate uniform random variables. All right. So how do you do that? So we look at a related problem where you have, let's say, Bernoulli p random variables. You're given say x1, x2, x3 and so on. You have a sequence of IID Bernoulli p random variables where p is between 0 but perhaps strictly less than half, strictly greater than 0 and strictly less than half. You're given access to as many Bernoulli P random variables as you want, and the goal is to use these to generate Bernoulli half random variables. All right. So you want some kind of a function that takes this sequence, say m Bernoulli P random variables as input and outputs z1, z2 up to zk, which are all IID Bernoulli half. Okay, so the goal is to transform Bernoulli P random variables into Bernoulli half random variables. One key point that makes things a little easier is that you fix k. So basically I ask you to generate k IID Bernoulli half random variables. For a fixed k, you are allowed to vary m as much as possible, as much as you want. Okay, but the goal is to understand what is the smallest m, what is the minimum number of Bernoulli P random variables that you need in order to generate a Bernoulli, in order to generate k Bernoulli half random variables. All right. Is the problem clear? Are there any questions? No, k can be larger than m.
Must be larger or greater than equal to m.
We'll see that in a little bit. The goal is to understand how small can m be if I want for a particular k. All right, but m in principle m can be different from k, and m need not just depend on k. We'll allow it to be variable depending on the realization as well. So think of this as you have a function that will output, every time you call the function, it will output a Bernoulli P random variable. You are allowed to make as many calls to the function as you want, but the goal is to output exactly k Bernoulli half random variables. Okay. So here is one algorithm that allows you to do that. I do the following. So I take two, so suppose I do the following. K is fixed. So k is given to you, but m need not be fixed. M need not be fixed. So you can make more calls to the function to generate exactly k random variables. Yeah, equivalently, you can think of it the other way around. Given m Bernoulli P random variables, how many IID Bernoulli half random variables can you generate? That's equivalent to this. Right? So you do the following. If xi, so the algorithm reads pairs of xi's at a time. Okay, so you want to generate, let's say, one Bernoulli half random variable. So you make a call to the function, make two calls to the function, to this g function, and if you get 0, 1, then you declare 0. If you get 1, 0, you declare 1. If you get 0, 0 or 1, 1, you don't output anything. You just output the empty string. I'm sorry?
You could use the second 0 1. When you have 0 0 and 1 1.
Correct.
You could use the second 0 for your next. You could put it as xi.
You could potentially do that, but I just want one particular approach, not necessarily the best approach. Okay. So if I get 0 0, I output the empty string. If I get 1 1, then I output the empty string. Okay. So if xi plus 1 is 0 1 or 1 0, I output a zi. If not, I call the function again. The next time I call the function, if I get 0 1 or 1 0, I'm done. I output 0 or 1 and stop. If not, then I again call the function and so on. All right. So the x string, if it looks something like this, then the z string would essentially be, so this is 0 1, it outputs 0, then you see 0 0, so you output nothing, and then you see a 1 0, so you output 1, and you see a 1 1, so you output nothing, you see a 0 1, so you output a 0. So at the end, after 10 calls to this particular function, the output would just be 0 1 0. So using 10 Bernoulli p bits, I've generated 3 Bernoulli half bits. Okay. But first, even before that, you have to convince yourself that these are indeed IID Bernoulli half random variables. So what is the probability that, say, Z1 is equal to 1? It's p into 1 minus p. That is that it? So what is the probability that Z1 is equal to 1? Okay, are you sure? I'm sorry? Potentially I could have got an empty string. I wait for as many empty strings as possible to get the first bit, right? So this basically my Z, to be more precise. This is my Z string, right? So I output a 0 or I output a 1 only if I get 1 0, but I could potentially have got multiple empty strings before that. All right. So now can you think about why?
You have like p square plus 1 minus p whole square as your ratio. P into 1 minus p by 1 minus p square minus 1.
So let's try to do it carefully. What all events contribute to Z being equal to 1? Okay. So first, I could potentially get let's see, 1 0, right? So I could get 1 0. So this is probability that the x string is 1 0 plus the probability that the x string is, say, 0 0 1 0, or the x string is 1 1 1 0, or the X string is say 0 0 0 0 1 0 and so on.
P bar 1 n plus 1 into 1 minus p plus p into 1 minus.
Sorry, let's do it carefully. So what was the first case? What is it? So it's p into 1 minus p plus so it's p square plus 1 minus p the whole square times p into 1 minus p, right, plus so it could be 0 0 0 0 0 0 1 1 1 1 0 0 and so on, right? Yep. Right, and so on. So this is equal to p into 1 minus p times summation I equal to 0 all the way up to infinity of p square plus 1 minus p whole square to the power I, which is p into 1 minus p times 1 by 1 minus p square plus 1 minus p the whole square. Correct? Correct. What is the denominator equal to? Correct. So it's p into 1 minus p times 1 by 2p into 1 minus p, which is just half. Right? Likewise, the probability that z1 equal to 0 is also equal to half. So it may so happen that you have to wait for a really long time to output the first z1. But no matter what happens, you will always, you're guaranteed that it's going to be Bernoulli half. Okay. And what can you say about z1 and z2? Yeah, okay. You want to? What can you say about z1 and z2? Are they dependent? They're independent because they're based on independent coin flips xj, right? So, which one? In this particular approach, this is one algorithm, right? I'm not saying that this is the best algorithm. This is some algorithm. So it's just to demonstrate that this is possible. It is possible to generate IID Bernoulli half random variables from IID Bernoulli p random variables. That's all. This is definitely not the best way to do it. So the goal is, so in this case, what can we say about the expected number of flips, the expected number of random variables that you need to see, the expected number of xi's that you need to see to output even z1. or let me ask the other problem. So if I give you n random variables, what is the expected number of Bernoulli half random variables that you can generate? And why is that?
It's geometric random variable.
Okay.
And the probability of getting a valid IID for not the random variable is 2 into p into 1 minus p. And the expectation of a geometric random variable is 1 by p. Here it's 2 into p into 1.
Okay. So in this case, what is the, like, how many valid ZIs do you generate? So when do you generate valid ZIs from the XJs? When you get either 0, 1 or 1, 0, right? So basically you can write this as expectation. So K is, let's say, summation I equal to 1 to n by 2 of the event that, let me, yeah, it's to I x to I minus 1 is 0, 1 or 1, 0. Sorry? No, I reframed the question to say that, yeah, I give you n flips, n Bernoulli p flips. Using this, I want to know what is the expected number of Bernoulli half random variables that I can generate. Okay. And this is basically for every pair. If it's either 0, 1 or 1, 0, I get one Bernoulli half flip. If it is 0, 0 or 1, 1, then I get nothing. Right? So in this case, in this toy example that I had over here, I could generate 3 ZIs from 10 X random variables. Okay. So this is just summation I equal to 1 to n by 2 of 2p into 1 minus p. So the expectation of k is basically just n p into 1 minus p, assuming that n is even. Alright, so you want to know if this is the best, and if not, what is the minimum number required. Okay. And we'll do so without looking at any particular scheme, but rather just using information theoretic inequalities. Alright. So we'll start with n times the binary entropy of P, which is nothing but just h of x1 through xn. Now I claim that this is greater than or equal to, or let's do it, put another step. So this is h of xn. This is equal to, using the chain rule, this is h of xn comma zk comma k plus because h of xn comma zk comma k is equal to h of xn plus h of zk comma k given xn. Right? I've just used the chain rule, nothing else. What can you say about this second quantity here? I have this fixed algorithm. I have some algorithm which is fixed, right? If I give you xn, how much uncertainty is left in zk and k? Yeah? It's 0, right? Because zk is a deterministic function of xn. Since zk is a deterministic function, the length k is also a deterministic function. Right? Any question? Is this okay? So this is 0. So the first, now I have the first quantity, h of xn comma zk comma k. This is equal to h of zk comma k plus h of xn given zk comma k. Right. Now this quantity is greater than or equal to h of zk comma k. Why? Entropy is non-negative. Okay, so I'll write this as h of k plus h of zk given k. We have just expanded the conditional entropy in this particular form. Now given k equal to little k, what can you say about h of zk? What should it be? What do you know about the zk's? They should be IID Bernoulli half, right? K times h2 of half, right? Because the length of zk is k. So this is, we know that the Zi should be IID Bernoulli half. So the entropy of Zk given k equal to little k should be equal to little k times the binary entropy of half, which is just little k. So this is the entropy of k plus, what is the second term? It's just expectation of k. The expected number of Bernoulli half random variables that you were able to generate. All right. And this quantity is greater than or equal to expectation of k. Again, I'm just using the fact that the entropy of k is non-negative.
So shouldn't k go from 0 10 by 2?
That is using that particular approach, right? So this sequence of inequalities holds true for any algorithm I used. I'm not restricting myself to that particular algorithm that I just talked about. Let's consider any arbitrary algorithm that takes n Bernoulli p random variables as input and outputs k Bernoulli half random variables.
But then you told k from 0 to n, which means you can't generate more than n much.
Yeah. Do you think it's possible? Okay, it doesn't really matter. You can allow k to go all the way up to infinity if you want. Right? It doesn't change anything. Because in the end, all I have is expectation of k. So the expectation of k is less than or equal to the binary n times the binary entropy of p. So on average, the number of Bernoulli half bits that you can generate is essentially equal to the total randomness in the source, which is n times the binary entropy of p. All right. This is kind of intuitive because in principle the total amount of randomness you're generating n IID Bernoulli half bits. Sorry, k Bernoulli half bits from n Bernoulli p bits. The total amount of randomness should still be preserved, right? The entropy of the bits that you've generated cannot exceed the entropy of the bits of the source, right? So the entropy should still be the same, and in this particular case, the expected number of bits, since the bits that you're trying to generate are Bernoulli half, the total entropy is essentially governed by the expected number of bits you can generate. Right. And so this is a specific case, but there are all other variants that you can consider. And overall, the principle still remains. The number of uniform random bits that you can generate cannot exceed the entropy of the source. In this case, we assume that the source was IID Bernoulli P, but you can get rid of many of those assumptions. It doesn't have to be Bernoulli, it doesn't have to be IID. If you have any source, then the total number of uniform random bits that you can generate is going to be not more than the entropy. Now, does there exist an algorithm that achieves exactly equal to this? Depends. All right. In some cases, for large enough n, you can. In most cases, if n is sufficiently large, there exist algorithms that allow you to generate those many IID random bits. For small n, may not be true. Right? Questions?
So this means that the previous algorithm is not.
How so? It's not, right? Because I would have had to go close to p into 1 minus p. This is not optimal. Question? Great. So what we saw in the last couple of examples, and also even before that, is that these information theoretic inequalities or these quantities can help us prove non-trivial lower bounds on some optimal quantity that we are interested in. The expected number of bits that you can generate, or the minimum expected compressed length, and so on. All right. So first we'll develop some more such tools that are far more powerful, and we'll repeatedly use them to derive such lower bounds on the optimal performance. In this in this little example that we saw, we didn't make any assumptions on what kind of compressor or what kind of functions were used, right? These inequalities hold true irrespectively of how you are mapping the xi's to zk, right? You're allowed any particular function. As long as there's no additional randomness that is introduced into the system, all of these inequalities hold true, and this gives you a fundamental lower bound. So the first we'll see is what is called the data processing inequality. Many of the fundamental inequalities that we derive are in some sense very intuitive, right? The fact that conditioning reduces entropy, and even the high level intuition over here that if you want to generate random bits, then the total entropy of the bits that you generate should be equal to the entropy of the source. All of these are quite intuitive, but how you use the specific set of inequalities requires some creativity. Right? For example, we started out with this particular quantity and then we cleverly used the chain rule. At first glance, it may seem like, oh, this is coming by magic, right? It's not, you don't realize why I do a particular sequence of steps, but you're able to follow every single step, and once you see the whole proof, you see, yeah, this is correct. But coming up with those steps is not, you still may not have that kind of intuition, but we'll see that there's the same flow. Once we see multiple such examples, you'll see that the approach is quite similar. Okay, but of course, proving lower bounds in general is hard and does require quite a lot of creativity. Okay. So the data processing inequality, basically the setting is the following. Suppose I have a random variable x. Yeah, question. So the entropy of zk cannot be any more than the entropy of xn. Because after all, zk is a function of xn. Right. Need not be equal. Yeah. It can't be any more than the entropy of xn. But also, if you wanted to do the best possible, right, you would want the entropy of zk to be equal to the entropy of xn. Right? Because then you're not losing any randomness, so to speak. But one thing you have to keep in mind is that k is not a fixed number. Right? K itself is random, it could vary. So what we wanted to do was connect expectation of k with the entropy of xn. And in this case, the expectation of k is equal to the joint entropy between zk and k. I'm sorry, it's upper bounded by the joint entropy between zk.
How do you infer that entropy of generator should be less than the entropy of your source from this?
Why is h of zk less than or equal to h of xn?
Yes.
Zk is a function of xn, right?
No, like from the last inequality.
Okay.
How did you infer that?
That's a more general statement, right? That if zk, I have any function zk which is some function g of xn, then the entropy of Zk is less than or equal to the entropy of Xn. You're asking why this is true?
No,
Huh.
from the expectation that the question, how do you infer that?
Okay, so this is not a rigorous statement as of now, but intuitively, suppose that k were not a random variable, all right, k was fixed, but still you wanted to generate k Bernoulli half bits. If you wanted k Bernoulli half bits, then the entropy of xk should be equal to what? K, right? The entropy of Zk would be equal to K if K is fixed, all right? And we know that entropy of Zk can't exceed the entropy of Xn. So K can't exceed Xn. That is if K were fixed. So intuitively, even in the variable length case, that should hold on average. That's the high level heuristics that was used. But in the end, all of this requires a proof.
So honestly, from the job definition of conditioning on ZK, because condition on, instead of conditioning on K,
Uh-huh.
we condition on ZK.
If I only conditioned on Zk, I would never get expectation of K. Because in the end, what I was really interested in was expectation of K, not the entropy of Zk. If I were only interested in showing that entropy of Zk is less than or equal to entropy of Xn, then yeah, that would have been enough.
Is that not like n into
Up to the first order, yes. But not exactly for every n. So in the sense that expectation of k by n, as n tends to infinity, this would be equal to entropy of P. All right, and that holds true in much more generality. Even if the source is not Bernoulli P, let's say I had some other source, which need not even be an IID sequence, I can still generate IID like Bernoulli half bits. Okay. Now, any other questions? Okay. So let's go to this, what I call the data processing inequality. The setting is the following. There's some random variable x that I want to estimate or infer something about. Okay, something that I want to learn something about. But I don't get to see the random variable x directly. I get to see a random variable y. All right. So the question is, suppose I use the random variable y to infer something about x. I get some kind of an estimate. Okay. Now, suppose I process y in some way. I take a function of y, or I add some other, I do some random processing on y to get another random variable z. Can z give me more information about x compared to y? That's the question that I want to address. All right. So basically I have x and y, two dependent random variables. Y is my observable. X is something that I want to infer something about. I can either directly infer something about x from y, or I can process y in some way to get z, and then use z to estimate x. So can z give me more information about x than y? That's the question. All right. Now I have to be a little more precise in what I mean when I say that Z is a processed version of Y. Basically what I'm saying is that X, Y, Z form a Markov chain. So I have three random variables X, Y, and Z such that X, Y, Z form a Markov chain. So the distribution of Z given X and Y is the same as the distribution of Z given Y. So conditioned on Y, X and Z are independent of each other. So if X, Y, Z form a Markov chain, Z, Y, X also form a Markov chain. The data processing inequality basically says that if X, Y, Z form a Markov chain, then the mutual information between X and Y is greater than or equal to the mutual information between X and Z. A DPI is data processing inequality. That's it. This is a short form of. The proof is fairly simple. Again, this is something that's natural, something that you would believe, because when you're processing Y to get Z, you're essentially either losing some information from Y or you're adding some information that is independent of X. Right? Only then can X, Y, Z form a Markov chain. So anything else that you do cannot really give you any more information about X than Y.
So can we change what the inequality codes if we take Z is equal to some function G of X, where G is a one-one function?
Agreed, yes. It's true that if Z is a bijective function, let's say, of Y, then equality holds, but equality holds in a more general setting. So holds if X, Z, Y is also a Markov chain. All right, and in fact, such a Z, all right, or to be a little more precise, if Z is equal to some function of Y such that X G of Y is a Markov chain, then Z is called a sufficient statistic of X from Y. So it holds true for any function which is a sufficient statistic. To give sort of a trivial example. Let's say that I have x, some random variable x, and y is equal to whatever x square and x square plus some noise. Or let's keep it even simpler. Right, so y contains two components, one which is x square, the other which is like pure noise. And I take z to just be equal to x square. Z is a function of y. It's not bijective because I can't recover y from z. But z contains all the information that I need about x. Yeah.
So why do you mean Z is called sufficient statistic of X?
So this is the definition. Right? Any function of y such that x, g of y and y form a Markov chain is called a sufficient statistics. Right? In particular, this z happens to be a sufficient statistic of x. It's a trivial example, but it is still something where z is not a bijective function of y. Any questions?
What happens if it's just one function, not like
Which?
G function? G
Okay.
of y.
Okay.
So G is not, it is bijective obvious. It's just one on one.
Huh.
So why would it not?
It would still be, yes, I agree. It would still
That
be
is
true. But something more, right? But for example, a sufficient statistic, the class of sufficient statistics is far beyond just one or bijective functions. This is an example where it's not a 1-1 function, it's a many to one function. That's the only point I wanted to make. Any other questions? Okay. The proof is fairly simple. Let's just consider the mutual information between x and yz. I'll use the chain rule of mutual information to expand this in two different ways. So this is the mutual information between x and y plus the mutual information between x and z given y. But what is the mutual information between x and z given y? What do I know about x, y, z? Markov chain. So what is the mutual information between x and z given y? It's equal to 0, right? Or if you want to be, if you want to convince yourself even of that particular fact, I can write the mutual information as h of x given y minus h of x given y and z. What is h of x given y, z? It's h of x given y because conditioned on y, x and z are independent of each other. Right, so this is equal to this particular quantity. So that's one way of expanding the mutual information between x and y, z. Another way of expanding this again using the chain rule is as the mutual information between x and z plus the mutual information between x and y given z. Now, the mutual information between x and y given z can be anything, right? but it's a mutual information, so it's non-negative. So I can say that this is greater than or equal to the mutual information between x and z. But when do I have equality? When the mutual information between x and y given z is equal to 0, and that can happen only if x, z, y forms a Markov chain. That is, x and y are conditionally independent given z. So the mutual information between x and y is greater than or equal to the mutual information between x and z. That's it.
Could you explain why you said this statistic?
So that's a definition.
Like, doesn't the sufficient statistic mean we're losing more information about the population?
We are. So the definition basically says that given g of y, x and y are statistically independent of each other. Right? So we know that x, y, g of y is a Markov chain because g of y is a function of y. Right? But in addition, x, g of y and y form a Markov chain, which naturally means that you don't need any more information about x than what g of y can offer you. Right? That's why it's called a sufficient statistic. Because whatever you need about x, g of y has all of it. Whatever whatever extra that y can offer you is kind of unrelated to x.
What if like z was x squared plus n?
Okay? You will have to say, does that form a Markov chain? I'm sorry, I'm guessing here you're saying y equal to x square. Is this what you're referring to? Z is equal to x square plus n. Okay, so this is the setting that you're referring to. Is that right? But now are x and y independent given z? No. Right? So z is not a sufficient statistic of y. So there's also a point regarding terminology. Yeah. Nothing. Yeah. It's not. They're not independent given. X and y are not independent given z. So z is not a sufficient statistic. Any other questions? Okay. So the data processing inequality is quite helpful, but also rather intuitive. The next inequality is called Fano's inequality. And again, it relates to quantities that in hindsight will seem a bit natural. The inequality will seem a bit natural, but the exact form is not something you would even expect. Okay. So again, the setting is the following. Let's say that I have a random variable x, and I have a y, and using this I find and estimate x hat. Okay. So x is in some alphabet x, y lies in some alphabet y, and x hat is an estimate that you produced, which also lies in the same alphabet as x. Now your goal is to essentially reconstruct x to the best form possible. So the quantity that we are interested in is the probability of error, which is the probability that x hat is not equal to x. It's a very general setup. I'm just saying that x and y, x, y, x hat are random variables which are jointly distributed according to some arbitrary distribution, but x, y, x hat form a Markov chain. In addition, x hat and x are drawn from the same alphabet. Okay. There is no assumption on the relationship on how the joint distribution of x and y should look like. There is no assumption on the joint distribution between y and x hat. It could be anything. Also, x hat need not even be a deterministic function of y. Okay, that's the very general setup. So in this case, so my goal is to derive a lower bound on the probability of error in terms of some entropic quantities. All right. And for this, I have h of x given y less than or equal to h of x given x hat, which is less than or equal to the binary entropy of the probability of error plus the probability of error times the log of the cardinality of x. Okay, so what is the high level intuition behind this inequality? While the exact form is something that it's impossible to guess, the right hand side is something that goes to 0 as the probability of error goes to 0. Right? You can see that. H of PE goes to 0 as PE goes to 0, and PE log cardinality of x goes to 0 as PE goes to 0. Okay. So suppose that I have some system, I have some estimator for which the probability of error is very, very small. Okay. Then what must it mean intuitively? It must mean that given x hat or given y, the amount of residual uncertainty in x should be small. If not, the probability of error should be large. Right? Because if there is a lot of uncertainty about x, given your estimate x hat, then the probability of error can't be small. Right? But Fano's inequality gives an exact bound, a quantitative relationship between these two quantities, the amount of residual uncertainty and the probability of error. All right. Any quick questions? Okay. The proof again is not really complicated. We'll define the error random variable, which is 1 if x is not equal to x hat, and it's equal to 0 if x equal to x hat. Okay. And as always, we'll start with some entropic quantity, which the moment it will appear as if it's coming out of like magic. I look at h of error x given x hat. Because eventually I want a quantity that looks like h of x given x hat. Right? That's a quantity that I'm interested in. So I have h of e comma x given x hat, which again, using the chain rule, I'll write this as h of x given x hat plus h of e given x hat. What can I say about the second quantity? It's equal to 0 because given x and x hat, you know whether you're in error or not. So this is equal to h of x given x hat. Okay, and we'll take h of e comma x given x hat and use the chain rule again to expand it in a different way. You see that there's a trend, right? We're doing something very similar all the time. Take the joint entropy and then use the chain rule to expand it in two different ways. That's a very common trick that we'll frequently keep using. This is equal to h of e given x hat plus h of x given e and x hat. Now, okay, now what do I want? I want to bring this to the form h of the binary entropy of E plus PE times log of cardinality of X. All right. The first one is a little easier to see why. Now this quantity is less than or equal to h of E. Yeah.
Then how you wrote X? That's it.
This one. I'm just taking this quantity and using the chain rule. Okay. Is this okay? Great. Now h of E given x hat is less than or equal to h of E because conditioning can only reduce entropy. I'll keep the other quantity as it is. But what is h of E? What is E? It's a Bernoulli random variable. And what is the probability that E is equal to 1? It's PE, the probability of error. Right? So the entropy of E is just the binary entropy of PE. Okay. All right. So now I have h of x given E comma x hat. I'll again write this as h of E given x given x hat comma E equal to 1 times the probability that E is equal to 1 plus the entropy of x given x hat and E equal to 0 times the probability that E is equal to 0. Okay. What can I say about the second term?
0.
Why?
E 0, x equals x hat.
Correct. So if E is equal to 0, then I know that no error has occurred. So x is equal to x hat. So second quantity is 0. The first quantity plus I have the conditional entropy of x given x hat and E equal to 1 times PE. So given x hat and that there is an error, what values can x take? Yeah? Everything except x hat. right? So how many values can it possibly take? Log cardinality of x minus 1. And so the entropy of x given x hat and e equal to 1 is at most plus log cardinality of x minus 1 times pe, which is less than or equal to h of pe plus log cardinality of x times p. Which one? You mean from here to here? Why? No, right? Because the entropy need not be equal to, given that there is an error and x hat, x may not be uniformly distributed. It's possible that some values of x are more likely than some other values of x. Right. So this is a fairly loose upper bound. So the entropy of x given x hat is less than or equal to the binary entropy of pe plus pe times log cardinality of x. Now I want to also show that this quantity is less than or is greater than or equal to h of x given 1. All right, and that basically just follows from the data processing inequality. So from the data processing inequality, the mutual information between x and y has to be greater than or equal to the mutual information between x and x hat, because x, y, x hat form a Markov chain. But what is mutual information between x and y? It's entropy of x minus entropy of x given y, and this has to be greater than or equal to the entropy of x minus the entropy of x given x hat. These two can be cancelled. Just rearranging the terms, I get that the entropy of x given x hat is greater than or equal to the entropy of x given y. So from what I have above, this quantity is lower bounded by entropy of x given y. Question? This only works for discrete random variables, I agree. Okay, yeah. So, one point here is that there's no assumption on y. X and x hat should be discrete, obviously, but really we are not assuming that y is discrete. It could potentially be continuous. Although we have not really seen all of the information quantities for continuous random variables yet, but the data processing inequality actually holds even when x, y, x hat are continuous. Data processing inequality. Fano's inequality requires x and x hat to be discrete, but absolutely no assumptions on y. Why not? So again, a trivial example over here. Let's say that x is whatever Bernoulli p. Y is a vector which is x, and z, where z is a Gaussian random variable independent of x. Okay, and x hat is just the first component of y, which is just equal to x. Now in this case, again, x, y, x hat, they form a Markov chain. All Again, it's a trivial example, but there can be much more complicated situations where this is true. For example, we will in fact see this when we get into channel coding and some of the other problems, where you will want to send a finite set of messages through a channel which is continuous. So what you receive is a continuous random variable, but you will decode the message, or you'll decode the received signal to one of the possible messages. So the decoded message and the original message are both discrete random variables, but what you see at the output of the channel is a continuous random variable. Right? So in this setting, y is a continuous random variable, but x and x hat are both discrete. Okay. Any other questions?
Here it's also a sufficient statistic.
In this example, yeah, it's a sufficient statistic. Any other questions? Okay. So we'll see a very quick application of this to source coding. All right. But source coding with non-zero probability of error. So let's consider the fixed length source compression problem, where you have xn. The goal is to encode this into a binary sequence ck, where k is fixed, and this is decoded to give an xn hat, where now xn hat could potentially be different from xn, but both of them come from the same alphabet. Okay, so now k is fixed. It depends on n, it can depend on pxn, but it is independent of the realization of xn. So for two different input sequences, the value of k cannot change. It has to be fixed length. So somebody gives you n, somebody gives you the joint distribution pxn. Your goal is to come up with this compressor and decompressor, or encoder and decoder, which compresses xn to a k length binary sequence where k is fixed. And of course, as always, since we are talking about compression, we want k to be as small as possible. But now k is fixed, so you're okay with xn hat being different from xn some of the time, but not all of the time, of course, otherwise there would be no point. So you allow some error, that is xn hat not equal to xn is the probability of error, and you want this probability of error to be small. Okay. Ideally, you want this probability of error to go down to 0 as n tends to infinity. But even otherwise, you just want the probability of error to be arbitrarily small. So in this context, we want to know what is the minimum rate of compression. How small can k over n be? When we analyzed variable length compression, we came up with a specific compression scheme and analyzed all of the properties. We derived an upper bound on the expected compression length, and for the same compressor, we analyzed a lower bound on the expected compression length. Since that's the best compressor, we know that if you consider any other compressor, the expected length can only be larger than that particular quantity. Now we're going to depart from that particular approach. We'll try to derive lower bounds without assuming what compressor you have. I don't even know what is the structure of the best compressor. Even without that, I want to derive a lower bound on the expected compressor, or a lower bound on k by n. Okay. So what helps us here is that xn ck xn hat forms a Markov chain. And the idea is to just use Fano's inequality. Okay. But it requires a little more than that. You can't just directly use Fano's inequality, because Fano's inequality only gives you something in terms of a conditional entropy. But my goal will be to connect the smallest k over n with the entropy of xn. So we'll start with h of xn, and because I know that Fano's inequality relates h of xn given xn hat with the probability of error, I'll try to introduce xn hat into this quantity. So I have h of xn, I'll add and subtract h of xn hat given xn. In fact, I didn't even have to subtract. So what is h of xn hat given xn? It's equal to 0 because we're assuming that the encoder and decoder are deterministic functions. All right. So this is in fact equal to this. This is 0 since encoder and decoder the encoder and decoder are deterministic. So this is just h of xn hat. Okay, maybe I should have done it a little bit differently. Instead of bringing in xn hat, I'm going to bring in ck. Same idea follows. Right? Ck is a deterministic function of xn, so the entropy of ck given xn is equal to 0. So this is equal to the entropy of xn given ck plus the entropy of ck. Right? But the entropy of ck is at most k. Right? Because ck is a sequence of k bits where k is fixed. Plus h of xn given ck. Now I can use Fano's inequality to say that this is less than or equal to the binary entropy of the probability of error plus the probability of error times log of the cardinality of x. Now to be a bit careful, because xn doesn't come from the alphabet x, it comes from xn, right? There are n sequences. So this is log cardinality of x to the n. Right? So this is equal to k plus the binary entropy of the probability of error plus n times the probability of error times log cardinality of xn. I'll use an even more loose bound, K plus, the binary entropy of P can be at most 1. All right, so this is at most 1 plus n times the probability of error times the log cardinality of x. Okay, I'm just doing this so that I get a simple form of the expression. So if I rearrange, remember that the left hand side was h of xn. I have the probability of error to be greater than or equal to h of xn minus k minus 1 divided by n times log cardinality of x. Or log cardinality of x times h of xn by n minus k by n minus 1. So if I want the probability of error to be small, then k over n can't be much lower than h of xn by n. Right? So if we want the probability of error to go to 0, as maybe n tends to infinity, then we would require the rate, which is k over n, to be greater than, or at least greater than or equal to the entropy rate of the source. In particular, if I take a memoryless source, then the right hand side is just entropy of x. So the minimum rate of compression has to be greater than or equal to the entropy of x. Just so that I can say something about the asymptotics. This lower bound holds true for every n, but the optimal rate of compression is lower bounded by whatever h of xn by n minus 1 by n effectively. All right, and it also depends on the probability of error. I could have, another way of rearranging this is that an equivalent version is that k should be greater than or equal to, or k over n should be greater than or equal to h of xn by n minus the probability of error times log cardinality of x minus 1 by n. Yeah. Upper bound PE instead of? Okay, yeah.
This is a lower bound.
Correct. So this is basically saying that no matter how you choose your compressor and decompressor, the probability of error is going to be at least something. Right? So this gives, it doesn't give, you don't know if this probability of error, if the right hand side can be achieved. But you know that no matter what you do, no matter how you design your system, this is a fundamental limit on it's a fundamental lower bound on the probability of error. So if you choose your rate to be too small, then no matter what you do, you can't achieve a smaller probability of error.
Then we can't technically say PV goes to 0.
Yes, but it's saying something else, right? If we want P to go to 0, then it is necessary to have R to be greater than or equal to this. It doesn't mean that, so it's a one-way statement, right? If P goes to 0, then this must happen. But just because this happens doesn't mean that this should happen. Okay? That's a good point. It's something to keep in mind. Right now, all we've shown is that if you have a system for which the probability of error goes to 0, if you have a compressor for which the probability of error goes to 0, the rate must be greater than or equal to the entropy rate. Or the asymptotic rate must be greater than or equal to the entropy rate.
Shouldn't it be like h of xl minus k should be 8 low penalty?
I'm sorry?
H of x, entropy of xl minus k.
Correct.
Little low.
Yes. Yes. So what is?
Why is the other limit as an
Okay. So firstly, it need not be little of n, because your k could be far away from the entropy. K could be much larger than the entropy. That will still potentially give you a vanishing probability of error. That will give you a low compression. It will give you a high compression rate, which is not desired. Agree. All this says is that if you want the probability of error to go to 0, this quantity, if it's too negative, it's fine. It doesn't give you anything terribly useful. But this quantity can't be very positive if you want the probability of error to be small. Right?
So this inequality just says that if you want the probability of error to be minimized, we cannot go beyond this compression.
Correct. We cannot go below this compression rate. So no matter what you do, so for any compression rate, for any compressor, hold on, 2 minutes. So for any compressor, the rate of compression has to be greater than or equal to the entropy rate plus the probability minus the probability of error minus 1 by n. All right? Any questions? Okay. So this kind of, again, we did this without any assumptions on, or without knowing what is the structure of the optimal compressor or decompressor. Right? Purely using these information theoretic inequalities, purely using entropy, mutual information, and Fano's inequality, we were able to derive a lower bound on the optimal compression rate. Also, what we've seen is that even if we allow a small probability of error, the optimal compression rate can't go any below entropy. So entropy is still a fundamental limit of compression, even for fixed length compression with small probability of error. Okay? All right, so let's stop here.